Alright guys, for the final section that we'll be covering for this chapter, section 5, we are looking at kind of the idea that this chapter started out with, but in reverse. We started the chapter by learning about some special angle names like alternate interior angles, corresponding angles, all that kind of stuff that you see in the list right here. And what we discovered in the second section was that if the lines that we're working with are parallel to each other, then all these special relationships started to happen between these pairs of angles. So if the lines were parallel, then corresponding angles are congruent. And if lines are parallel, alternate exterior angles are congruent, so on, right? But the way that we were looking at all of those all had to do with if the lines were parallel, then all this stuff is true. Well, what we're looking at in this final section is just the opposite of that. If we can prove that any of these relationships are true, then we know that the lines are parallel. So we're doing the converse of what we started out with. So remember, the converse is where you switch the order of your if-then statement. And so for these guys, we are looking at the converse of the theorems or the postulate that we're going to be looking at. One of the things that I do want you to take away from this is you will need to know the difference between the theorem and the converse of the theorem. Because like in a test question or something like that, you're going to be asked to state a reason for how you know what it is that you know, right? And so that reason could potentially be a theorem or a postulate, or it could be the converse to the theorem or the postulate. So you do need to know the order in which these things are applied. So for this final section, again, the converse of all of these, anytime you are dealing with the converse, will be the times where you are trying to prove that the lines are parallel. Okay, we don't know that to begin with. That's what we're trying to prove. So if you look at the first example, so one of the first things that they're starting us out with is what can we prove, what lines can we prove are parallel if we know information like this, right? So if I look at angle 1 and angle 2, which lines would have to be parallel if angle 1 is equal to angle 2? And so let's cover up the line that's not being used and just look at the lines that are being used for this one. All right, so let's just focus on the lines containing angles 1 and angles 2 for this. So just like I did with previous section, it really helps in diagrams like this to sort of get rid of the line that's not being used, so it's a little more clear as to what we have going on here. So if angles 1 and angles 2 are congruent, then which lines would have to be parallel? Well, if you look at angle 1 and angle 2, we learned earlier section that angles 1 and 2 are called corresponding angles. So if corresponding angles are equal, or if corresponding angles are congruent, then the lines containing them, like R and S, would have to be parallel to each other. So M in this case is the transversal, because that's the line that they both are connected to, right? And then because they are equal to each other, that must mean that angle R is equal to angle S. And so that's what we're going to see on this. But if we need to state the postulate or theorem that we're using for this, well, this is the corresponding angles postulate, but it's the converse of that, because now we're using it to prove that the lines are parallel. So we're going to say the corresponding angles postulate converse. Right, so we're throwing in the extra C at the end there because this is now the converse of that postulate, since we're using it to prove the lines are parallel. One of the other things we'll be doing with these is a little algebra. So if you look at these guys, so again, what must be true about this and this in order for M to be parallel to N? And so the way we would read one of these statements is if you look at these two pieces of information for these angles, we know those as alternate interior angles. And so we could now say, if alternate interior angles are congruent, then the lines are parallel. Right? So then the lines are parallel. So if 3x plus 10 is equal to 6x minus 20, then M would be parallel to M. So you see how this is kind of working in reverse here, but it's really the same, all the same information. It's just the order in which we're applying these theorems or postulates. Okay, and so they went on to solve this one, so you'll have this for your example. As always, make sure that you read careful. Don't stop at solving for x if they are asking you for something more. So you'll notice on this one they had to plug it back in to actually find the measure of angle ABC. So let's try a few on our own here. All right, so as I look at these guys, first thing that we would notice right off the bat is what that relationship is called. Those guys are alternate exterior angles. And so we know by the alternate exterior angle theorem that these guys, when we're dealing with parallel lines, these guys are equal, or they're congruent. So as I look at this, we're going to say, this is like the one we just did. So it says find x so that L would be parallel to M. Right? So we're going to see this as if 5x minus 5 is equal to 6x minus 20, then line L would be parallel to line M. Right? So if these guys are equal, so what must x be in order for this statement to be true? So we're just going to go on and solve for x. So if I start by subtracting 5x from both sides, that would put me right here. I'm going to add 20. So the way we would read this would simply be, if x is 15, then L is parallel to M. Right? So that's kind of the order that we're seeing this because of the converse. So we are now proving that lines are parallel instead of the other way around, which is what we did in section 2. So when it does say identify what we used the alternate exterior angles theorem converse. So alternate exterior angles theorem converse. You're welcome to write all that out, but I think if we can throw in the letters to abbreviate it, I think we all now know what those mean. So let's keep moving on here. So let's jump over this one. This one was one that we don't run into a ton, but it did come up in an earlier section. We pointed it out in the lesson and in the notes, and that was the last item on this list up here. So this is one we have not talked about nearly as much, but if you have two lines that are perpendicular to the same line, then those lines must be parallel to each other. Right? So as you look at number 3, we're trying to show that L is parallel to M. Well, if M is perpendicular to the transversal, then in order for this line to be parallel to this line, then this one would also have to be perpendicular to that guy, right? And so what we're seeing is if line L is perpendicular to this line, and line M is perpendicular to this line, then that must mean that these two guys are parallel to each other. If they're both perpendicular to the same line, then they have to be running the same direction. They have to be parallel to each other. So in order for that all to be true, 3x plus 15 would have to equal 90 because the lines are perpendicular. So if we do a little subtraction on that 15, we're going to get 75, divide by 3, and we figure out that x is 25. So let me show you this one real quick. This is what we talked about in an earlier video. So on the bottom of page 182 in your book is the theorem that I'm talking about right now, right? So it's the converse of this theorem, right? This theorem said if the lines are parallel, so notice what they're starting with. They're saying if the lines are parallel, then the rest of this information is true. But what we're doing in this problem is we're saying if this is true, then the lines are parallel. And so now we're looking at the converse of this theorem. So we could say, you actually have two options for this. So we could say I'm using the perpendicular transversal theorem converse, which would be fine. So I could say perpendicular transversal theorem converse, or someone else might have looked at this and said, well, hey, that's a right angle. So if that's 90 degrees and that's 90 degrees, these are alternate interior angles. And so you could actually use that as a reason as well. You could also say the alternate interior angles theorem converse also tells me that this equals to 90. So we could have applied either one to this case. As you're looking some of these up in the book as well, I'm just going to say alternate interior angles theorem converse. A lot of times in the book on these, they'll just say it's the theorem. They won't even mention at this point that we're using the converse, because they just want to make sure that you have a reason to support the equation that you're setting up. When it comes to doing a proof, or when it comes to doing a problem like this, where we are actually proving that lines are parallel, then we want to make sure we throw in that converse. But a lot of times for the algebra, like what we're doing right now, they're kind of a little relaxed on whether you put the converse or not. So just an FYI. So this one could have been that theorem, or we could have said the perpendicular transversal theorem converse. So we could have gotten away with either one on that. Here's another alternate interior angles theorem converse. Right, so again, we're going to set this one equal to this one, and solve for x, and go on. So we're going to jump over that one because it's really not a whole lot different than this one. And the one that we looked at here, this is just another alternate interior angles theorem converse problem. So let me go on to this guy, which is at least a different reason than the rest of the group so far. So as I look at number 6, we want to recognize these are corresponding angles. And so if corresponding angles are congruent, so if 5x plus 20 is equal to 70, then line L is parallel to line M. Right? And so if I solve this, we're coming away with x is 10. So we're going to say basically if x is 10, then line L is parallel to line M. And so really we would call this the corresponding angles postulate converse. To do something like that. Remember that of the group, the corresponding angles is the only one that's the postulate. The other main ones are all theorems. You'll also notice that you're seeing up here on this one, just like I was talking down there, sort of the connection between these alternate interior angles as well as the perpendicular transversal theorem. Right? They're strongly linked for the same reason we were just talking about with this guy. Right? Because I could, like we said, I could get away with using either one based on the information that I'm given right now. So it's only true, of course, if I'm dealing with the perpendicular lines, right? So when I see the perpendicular lines, then we can often justify either reason in a case like this. Well, let me jump to the second page, final page, and let's take a look at a proof here. So proofs aren't going away quite yet. We still have some more time with proofs. Chapters 3 and 4 still deal heavily with proofs, so we'll be hanging out with these guys still for a little bit. So I want to make sure we know how to do these still. Here we go. Always, the given information. Right? We know to start with that. So I'm seeing 1 is congruent to 2 and 1 is congruent to 3. Automatically, that should jump out at you guys that we are seeing a little transitive property taking place. Right? This is one that's been going on for a long time for us now. But if angles 2 and 3 are both congruent to the same angle, that must mean that they're congruent to each other. So in second line, we're seeing that angle 2 and 3 are congruent to each other by the transitive property. And so here's the new one. Look at what we were trying to prove on this one. We were trying to prove that the lines are parallel. And anytime you're doing that, you got to be thinking converse, right? So I'm thinking the converse of this statement. So as I look at this from here to here, look at angles 2 and 3. Within that drawing, we want to recognize that those are alternate interior angles, right? Alternate interior angles. They are on the inside of this line and this line, and they're on opposite sides of that transversal right there, right? So those are alternate interior angles, and we just proved that they are congruent. So the converse says, if alternate interior angles are congruent, then the lines must be parallel. So now I can say for certain that AB is parallel to DC because of the alternate interior angles theorem converse. Notice on this one, they didn't use the title. They literally wrote out what the theorem says. And that's acceptable, right? We can either use the name, or you can simply write out what the theorem tells you, right? Those are both acceptable. Oftentimes, way more often than not, the book will simply use the title rather than actually write out the entire theorem. But we could do it that way, right? We could do it either way. So you can just simply write out the entire theorem, or you can give the title of the theorem. But we do want to recognize that this is the converse, right? Because we started with congruent angles and we ended with parallel lines, and so rather than starting with parallel lines. So let's try one on our own here, now that you've seen one. And so right off the bat, if you were doing something like this at any point down the road, look at what you're trying to prove, right? If I'm trying to prove that lines are parallel, right off the bat, I'm going to be thinking converse, right? Because I'm trying to prove that lines are parallel. So as I look at my given information, 15 is congruent to 5. And again, guys, just like you saw in the one up above, it's certainly fine to put the entire given in the first statement, but sometimes the book doesn't always do that. They fill it in when they actually use it, and that's fine too. And so we could go either route with this, but of course we want to recognize this was given information. 15 really helps to mark your diagrams on this, by the way. So here's 15, and here's 5. So if you take a look at the next statement, where did this come from? Right? It didn't come from the given. 13 is nowhere mentioned up here. But where could it come from? Look at the diagram for a minute. Look at 13 compared to 15, right? So hopefully we all recognize those guys as vertical angles at this point. So we know by the vertical angles theorem that 13 is congruent to 15. By vertical angles theorem, and again, let's mark that. And here's why I always say to mark this stuff, is now something should stand out to you, whether it be through your markings or through the statements that were just used. We should now recognize, hey, look at my markings, right? According to my markings, 5 and 13 are congruent to each other with everything that I just marked. So where is that coming from, right? As I look at the previous statements, here's our ever famous transitive property, right? We know that if 5 and 13 are both congruent to 15, then they must be congruent to each other. So here's our transitive property, right there. And so now, if 5 and 13 are congruent to each other, that must mean that line R and line S are parallel to each other. And how do we know that? So if you look at the relationship between 5 and 13, we recognize those as corresponding angles, right? And so the converse that we've now been learning today is that if corresponding angles are congruent, then lines must be parallel, right? And notice I'm using the two lines that they are connected to. Neither one are connected to line L, so he should not even be in the picture. So I know it's not giving me those two lines, right? It's got to be two lines that they're both connected to. And so in this case, R and S are parallel to each other. And for this, you could write out the entire statement, and you could say, if corresponding angles are congruent, then lines are parallel. And if you want to write out the statement, that's totally fine. Or you could recognize that, hey, we just proved lines are parallel. That's the corresponding angles postulate converse. Right, and so we can write that too, sort of abbreviate it. Notice the final use of our given information. So now they're bringing in 1 and 5. All right, that was the rest of our given information. Well, if you take a look at 1 and 5, so here's 1 and here's 5. And just to make this stand out, I'm going to give these guys a different marking. because I want you to see what's taking place right now. So just look at the pink ones for a minute. Ignore the blue ones. This is really separate from the rest of the proof. They were kind of trying to squeeze in, I think, as much information as they could within one proof for you. So that was given information. So if angles 1 and 5 are congruent to each other, what else would we know? Well, notice that these are both connected to L and M. So now we can say line L is parallel to line M because the corresponding angles are congruent. So here's the converse again of the corresponding angles. And again, notice they just wrote out the whole thing instead of the title, which is fine, but that is it for now. We'll be getting plenty of practice with these proofs, but that is the end of chapter 3 for us.